My name is Andreas Musolf. I'm coming from the Helmholtz-Centre for Environmental Research, and together with Guillaume Nord and Ute Weber, I'm convening this session number 8 on extremes in the critical zones. And our keynote speaker is Nils Hovius, who's already waiting there. And Nils is from the Helmholtz-Centre for Geoscience, and he's heading the geomorphology group there. And Nils is a geomorphologist and will report about extremes in geomorphology, fitting to our session. And so Nils is working on geomorphology, and I have to look up what else he's doing. Landscape evolution, and also reaching out to socioeconomy, which I find very interesting. And Nils spent his career partly abroad in Netherlands and Ireland and UK and US, and visits in like different universities, and is at the Helmholtz-Centre for Geoscience since 2012. I hope I'm correct on that. So quite a while already. And yeah, Nils, so is the presentation already there? Probably. So Nils will talk about extremes, so I'm extremely happy and interested in this talk. Nils, welcome.
Thank you.
The floor is yours.
I'm extremely grateful for the invitation and for you turning up this morning in large numbers. I'm also extremely grateful to actually follow Sebastian's talk, which was an absolutely stunning illustration of the real power in equipped observatories. I'm going to take you to another extreme, a very data-poor environment. Extremes. We can think about extremes in many different ways. In the first instance, we're human. We think of them as unfamiliar, unexpected, threatening situations. We can think about the impact extremes may have in terms of damage to our system, changing the dynamics of our system. We can be more dispassionate. We can look at the statistics of events, and we can find extremes in the tails of distributions or outside of normal distributions. And we can consider that extremes have an impact on the dynamics of coupled systems, for example, by exceeding thresholds, by connecting domains, by causing cascading effects, or by tipping the system into a different state. Now, what you see in this picture here is an extreme event. This is an extreme event in Uttarakhand province in northwest India in 2021. If you would stand here, you would observe the normal background situation. If you would stand here, you would observe something completely different. If you have no understanding of this situation here, then you don't know whether this is an extreme or not. Here it's evident that this is an extreme event. In many cases, you actually need to know the norm in order to understand the extreme and to explain the extreme and to understand the role of the extreme in the system. Now, one can take different perspectives to this. I've been introduced to you as a geomorphologist. I'm actually mainly going to talk about water. This conference very substantially focuses on water. Water plays a role in just about everything in the critical zone. Despite what you've just seen, actually there is a very limited understanding of the dynamics of water in mountain environments, especially in the extreme mountain environments that dominate the uppermost topography in our planet. And so I'm going to try to dig into mountain water, focusing both on the extremes and on normality. I'm going to try to establish normality first and then look at the extremes. We'll do this in a data-poor environment that is extremely important in terms of the global water cycle, in terms of global matter cycles, in terms of providing water to many, many millions of people. The Himalayas. The Himalayas are affected by climate change, and a large part of the scientific and political community are actually focused on the demise of the cryosphere in the Asian or the Himalayan water towers. What we know, however, is that the bulk of the water that actually discharges from the Himalayas, 2/3 or more of that water, comes through the groundwater system. And so understanding the groundwater system is fundamentally important to understanding water fluxes, matter fluxes under normal and extreme conditions. In some places, we have a detailed picture of the subsurface and its groundwater system in hilly, mountainous environments. In many places, we know absolutely nothing about this. And so our very naive image of that is kind of captured here with a ridge and valley topography covered in a thin layer of highly permeable and discontinuous regolith, underlain by a bedrock core containing some water. We have found by now that a system like this cannot be modeled with a one-layer behavior. It has to have multiple layers. More than that, for the Himalayas, is in most places simply not known. I'm going to take you to central Nepal, to the Botakoshi River, which is a trans-Himalayan river, and we're going to focus on a small tributary catchment which sits below the glacial equilibrium line altitude at the boundary between the high Himalayas and the lesser Himalayas, covering a drainage area of about 33 square kilometers with an altitude range of more than 2.5 kilometers, an average topographic slope, local topographic slope of about 33 degrees. This environment has more extreme topography than what you've just seen from the western US. We're going to see whether we can find commonalities there. It has permanent discharge here at the very base of the channel in the trunk valley. In many other places, the discharge is ephemeral. One of the beautiful aspects of the Himalayas is the fact that it has a very simple water off, water on climate. There's a long dry season with hardly any precipitation, and there's a long wet season with an awful lot of precipitation. The Kola, the small catchment that I introduced, sits right on the orographic maximum of precipitation and receives about 3.5 meters of rainfall per year, 80% of which falls during that monsoon and post-monsoon wet season. In this graphic, you see the precipitation, and you see that in the pre-monsoon there is a substantial amount of precipitation, about 20% of the annual total, but it doesn't actually solicit any water discharge or any change in water discharge in the trunk streams in this landscape, in contrast to what we see later during the monsoon and the post-monsoon. That is the case, that was the case in 2017, that is the case in many years. We see this behavior of a non-coupled and then a coupled precipitation and discharge system in many places in many years. And we estimate that about 400 to 600 millimeters of cumulative precipitation is needed for this landscape to become wet enough for it to be coupled, for the precipitation to actually result in any discharge increase whatsoever. Now, how does this work? There must be a lot of water storage in this landscape. Where is it and what is its dynamic? We're going to use methods, geophysical methods, that are in parts similar to what you've seen before, in parts different. The first one we're going to use is ambient noise correlation. This is a little bit like knocking on a watermelon and using the tone to actually judge how juicy that watermelon is. If there is more water in a landscape, then basically the seismic velocities, the waves that travel through this landscape travel at a lower speed. That is demonstrated here in this plot from Clement and Denol, where you see in blue the water level measured, and in black you see the seismic velocities, but inverted here. So basically, as the water level in this landscape decreases, the seismic velocities increase. The negatives are here, up here, and the positives are down here. So more water in the landscape, lower velocities. We had a set of seismic stations in this small catchment for reasons that have something to do with an earthquake that happened in 2015 in this area, and we'll return to that towards the end of this talk. After the earthquake, under what we assume to be normal conditions, what we see is that in the dry season, the seismic velocities increase gradually as the background discharge, the base flow, decreases gradually from this landscape. That trend persists actually into the pre-monsoon, when significant rainfall is not associated with an increase in the water levels in the river, and it is also not associated with an increase in the groundwater level. In fact, the groundwater reservoir continues to be depleted. And then there's a very sudden switch point right here when the seismic velocities drop, and this is the point where the precipitation and the water discharge in the trunk stream actually connect. This is the point where precipitation reaches the groundwater reservoir, and the groundwater reservoir gets forced at a higher rate and discharges into the channels. This persists during the monsoon season. Towards the end of the monsoon season, there is a water extraction, probably due to vegetation, and then we enter the dry season of the next cycle, and we see this same pattern repeated. Now, one interesting aspect is that when you look at the soil moisture in the top meter in the neighborhood, in the environment of these seismometers, and what you see is that soil moisture is low during the dry season, it is high during the wet season, it's stable here, stable there, and it rises during the pre-monsoon period. And the point where the soil moisture stabilizes is the exact point where the seismic velocities drop and where the precipitation and the river discharge become coupled. So the soil moisture in that top meter is like a gatekeeper. When that top layer saturates, and it may not be a meter, it may be more, it may be less. When that top layer saturates, then the whole system becomes coupled. Now, I already said that a one-layer model doesn't actually reflect the behavior of this system. A two-layer model does, and a two-layer model requires a threshold amount of precipitation that has to be added into this landscape in order for this model to actually match the observed behavior. This then leads to a concept of a top layer with variable saturation that at some point transmits water into the deeper groundwater system. The deeper groundwater system rises, the discharge increases from that deeper system, but there is extraction through transpiration of water from that deeper system during the wettest part of the year, and then gradually you go back into a drier condition. This is much like what we know from places we know a lot better. And so that's really convenient. In fact, the hydrology, the textbook hydrology that we apply in many places and that we assume to apply in many places also applies in this utterly extreme environment of very steep topography, very shallow bedrock, and low conductivities. It applies, we find this not only in the Kahula, but in fact also in seismic data from an array of, a French array, the High Climb Array, which was installed in the early 2000s, further west in the Himalaya, crossing the Himalayas right here, and we see exactly the same seismic velocity annual pattern with a rise up to more or less the start of the monsoon, a precipitous drop, the wet monsoon, and then we rise into the next cycle. So this appears to be ubiquitous. If we look at that top layer and how it functions in more detail, one of the remarkable things that we find is that the infiltration capacity of the surface in these bedrock mountain environments is incredibly high. We measure infiltration capacities with an average of 80 millimeters per hour. That exceeds most or all of the precipitation, even under extreme monsoon conditions in the Himalayas. So even under the most extreme conditions, if rainfall doesn't completely saturate this top layer, water will disappear into the subsurface almost in its entirety. The infiltration or percolation rates decrease by about an order of magnitude in the first meter, but remain very high with an average of 4 millimeters per hour, where the average here of the precipitation in this catchment is about 2 millimeters per hour. So only under the most extreme conditions does the precipitation actually generate surface runoff. That is, extreme rainfall rates or extreme rainfall duration. If we look with the techniques that have already been introduced, electrical tomography, resistivity tomography, at the structure of the somewhat deeper subsurface, we find a pattern that is actually not dissimilar to what you've seen in the first talk. Under a ridge, we find a core of high resistivity bedrock, which is covered by a layer with lower resistivity that we find in the pre-monsoon, in the monsoon, and in the post-monsoon. So no fancy animations here. Instead, just 3 snapshots of 3 different states of the topography during the annual precipitation cycle. The difference between the pre-monsoon and the monsoon is depicted here, and we can see a wetting extending about 10 to 20 meters into the subsurface in a laterally continuous layer. That layer turns into a drying layer if we difference the monsoon with the post-monsoon. So there is a rapid response of the top layer to the ambient precipitation. What we see below is that this core of the ridge actually continues to experience a wetting front that propagates downward long after monsoon precipitation has ceased. We find a very similar structure in hollows. That's the other extreme form in the topography here. This is a landslide hollow, and we traverse it horizontally. And we can see here again low resistivity at the top for about 10 meters. That wets during the pre-monsoon and that dries after the monsoon has ended. But what we see is that there are very distinct, very wet zones right here in the lowest parts of the topography, but sitting mostly below the topography. So these are subsurface channels that actually appear to be persistent through at least this time interval that we observed, and probably during the year. When we look at the flow in the overlying gullies, then what we find is that that water conduit sometimes intersects the surface and sometimes it doesn't. During the monsoon, we see water flow at different elevations within this gully system, but we see that at the end of the monsoon system, when rainfall ceases, rapidly the water disappears from this gully in all positions over a matter of weeks. That means that basically the water system subsides within this topography. It doesn't go dormant, but it doesn't intersect with the topography anymore. In contrast, in the trunk valley, all the way at the base of this topography, we see year-round discharge, which is here fed by deep groundwater discharge that only connects with the surface in that lowest part of the system. Now, this is a picture that persists across scales. If we scale up to a trans-Himalayan river here, the Kaligandaki River further west in Nepal, then we find that base flow is persistent through the year, and it scales with the size of the catchment. Distance to the outlet on the horizontal axis. Here's the river profile with a very marked nick point right here. This is the surface area of the catchment, and you can see that the base flow actually tracks that surface area of the catchment quite beautifully. That base flow comes from deep groundwater discharge. Now, how is that discharge organized? Christoph Annemann, some considerable time ago, actually went down this river and sampled or measured the activity of short-lived 222 radon, which is a measure of the contact of water with substrate in groundwater, but it could also be produced in the riverbed. Now, the production in the riverbed is very low. It is no more than 100 becquerels per cubic meter. And what we find is that the radon activity in the stream at all points sits in a domain that is actually considerably richer in 222 radon than what the in-river production would provide. We also know that radon disappears from the river at all places very, very quickly, and at the reach scale, there's almost a complete loss. according to our estimates, so that the high abundance of radon that we actually measure in the river is due to radon gained within the reach. And that is, as I already said, not due to interaction with the riverbed, but it must come from groundwater outflow. And so what this shows is that groundwater outflow is ubiquitous along the entire river. It is not a large amount in one place, a large amount in another place, and a lot of quiet in between. No, it is in many, many different places. Now, if we look at base flow amounts as a function of drainage area for rivers across the central Himalayas, then we find a very uniform behavior with an upper limit to the amount of base flow in the stream as a function of the drainage area that is probably determined by the limit to the amount of water that can be stored in the bedrock landscape. The size and the permeability of that bedrock landscape will have something to do about this, but that is pretty uniform across this domain. What we see is that in a given catchment, the base flow may drop below this level, and that reflects a recharge limitation. If there is less precipitation into that system, then basically it may be that the storage capacity isn't used in its entirety. This actually signals a sensitivity to climate. If climate becomes drier, then what is necessary to replete the storage that is discharged during winter, then basically we will see a drop-off of the base flow discharge. And this actually is, in a way, the lifeblood of these mountain environments, but also of the plains below. During the monsoon, there is ample water. It is the base flow that actually determines year-round security, and this is what should be understood better. Now, that storage capacity that we've seen now in many rivers in the central Himalayas is not a constant. It is affected by, for example, seismic boundary conditions. And that is illustrated by what happened during and after the magnitude 7.8 Gorkha earthquake in 2015 in central Nepal. The data that I've shown you are mostly from this little catchment right here, which sits in the footprint of strong ground motion associated with the main earthquake, but also strong ground motion associated with a very strong aftershock, a 7.3 aftershock months later. What we see for 2015, then, if we revisit the seismic velocity data, is a deviation from the picture that I've just shown you. So this is 2015. The picture that I've just described to you is from this. So if we extrapolate this picture either with a model or we take the average observed behavior and plot it right here, then we see that the measured seismic velocity in 2015, shortly after the earthquake, actually drops much below this. This means that the velocities are lower due to either a distension of the rock mass and or a greater abundance of water in that rock mass at that particular time. Now, the climatic conditions were not exceptional in that year. In fact, it was a relatively dry year. What we see, though, is that immediately after the earthquake, or during the earthquake, the water level in the river at the nearest gauging station just jumps up by about 30 centimeters. The topography drains. In fact, the epicentral topography lost several cubic kilometers of water in this episode. What we also see is that subsequent to this, the summer actually has very limited rise and fall of the river level compared to other summers with similar precipitation. That means that a lot of the water that falls in this landscape actually stays in this landscape, probably refilling the storage that was depleted and maybe also filling excess storage. That transient lasts for about 6 months. After 6 months, our hydrological model and the observed data do converge again. So this is a transient, it's a relatively short transient, very short on the time scale of the return of perturbations, seismic perturbations of this scale. Not all water in landscapes like this comes from precipitation. There are pent-up reservoirs that are actually perched and sometimes breach and cause really the most exceptional floods that occur in mountain landscape. What you see here is a small glacier lake outburst flood that occurred and trundled through our little seismic network in the Botokoshi River in 2016. It is not the outburst from this big lake right here, but it's the outburst from a small lake right here, which was hit by a little debris flow. Water was pushed out and started gushing down the valley at a speed that was higher than the speed of the normal background discharge. So this little flood actually gathers more and more water from the river and from the landscape, not only water but also sediment, and it actually builds into a raging torrent like what I showed you on the first slide. Events like this are completely out of the normal distribution of discharge in rivers like the ones that I showed you for the Himalayas. So this is the normal distribution of discharge values, where here at the top end we have a return time of 75 years. What is marked here in the blue line is the discharge with a return time of 30 years right here. That's about the return time of these glacier lake outburst floods at this particular location. So for 2 glacier lake outburst floods, we have reconstructed the discharge, and that is plotted right here. You can see that in this top reach of the river, these discharges are from a different planet. They don't belong at all to this distribution here. And that means that I have an exceptional role in the geomorphic system in this particular place. What they do is they rip up, they destabilize the normally locked bed of the river, which is locked by the presence of very, very large debris blocks. And everything gets mobilized. That means that the bedload transport actually increases catastrophically. We estimate by a factor 30 in the immediate aftermath or during the flood, and it subsides over a period of about 2 weeks back to normality. In this time, this bedrock channel is unlocked. It actually changes. It incisors, it becomes wider, it changes its sinuosity, it undercuts valley sides, and it triggers mass wasting that propagates up the hill slopes. So this is a true extreme event of the black swan variety that, that actually propagates deep into the landscape, and actually it does affect all aspects of the critical zone, not only in the channel, but also on the surrounding landscape. The groundwater system otherwise appears to be quite resilient in these high mountain environments due to the long timescales and the large volume of water that are involved. But it may be prone to effects of climate change, both wetting and drying. Wetting in terms of exceeding or coupling between the precipitation and the discharge at an earlier point. Saturating the system at an earlier point, pushing more water through, drying in terms of actually decoupling the precipitation from the groundwater and the river discharge altogether. All of that plays against the backdrop of normalcy, where the picture we find in this extreme mountain environment is actually pretty similar to what we know from hydrology in most other places, with the exception that the infiltration capacity of the surface in this and many other places in high mountain environments is extremely, extremely high. That water that infiltrates feeds into a 2-layered system with a gatekeeper top layer and a long-lived bedrock groundwater reservoir below. The storage in that deeper reservoir is limited by the volume of the bedrock that is available within that topography and the rate of recharge, and groundwater drains out of this deep reservoir ubiquitously and persistently in all trunk streams. Thank you for your attention. And do remember that the normalcy actually is the key to understanding the extremes now.